Hello, everyone. Tonight, we will embark on a journey to the mysterious glaciers of Europa. Enjoy listening. Europa is one of those rare places in space where the question, could there be life, doesn't feel like pure fantasy. It feels like a careful scientific problem with real physical parts: water, energy, chemistry, and time. What makes Europa so compelling is not that we have proof of organisms, but that we have multiple, converging reasons to think it may offer something life needs most: a long-lived ocean in contact with an active world. Let's walk through what we know, what we suspect, what the newest observations add, and what the next missions are truly designed to answer. Europa, in one calm sentence. Europa is an icy moon of Jupiter that very likely hides a global salty ocean beneath its surface. And that ocean may have the ingredients and energy sources that could make it habitable, though whether it is actually inhabited remains unknown. What scientists mean by life on Europa. The phrase life on Europa can sound like a single yes or no question, but in science, it usually splits into two quieter questions: habitability versus inhabited. First, is Europa habitable? This means, does it have environments where life as we understand it could, in principle, survive and reproduce? Second, is Europa inhabited? This means, did life actually begin there, and does it exist now? Europa can be very promising on the first question, while still being uncertain on the second. Earth is our only confirmed example of life, so we don't yet know whether life emerges easily wherever conditions are decent, or whether it's extremely rare even in good environments. What life is most likely to look like there? If life exists on Europa, the most realistic expectation is microbial life organisms powered by chemistry rather than sunlight, potentially similar in broad concept to some Earth microbes living deep in oceans or within rocks. That does not mean it would be identical to Earth life, but it gives a grounded starting point: small, chemically driven, adapted to darkness, and possibly slow growing. The strongest pillar, Europa, almost certainly has a subsurface ocean. Europa's surface is bright water ice, crisscrossed with dark lineaments, long cracks and bands that look like the shell has been stretched, fractured, and partially resurfaced. The surface itself is already a hint that something dynamic is happening below. Evidence from magnetic measurements, a conductive layer under the ice. The most persuasive evidence for an ocean comes from the Galileo mission, 1990s. As Europa moves through Jupiter's powerful changing magnetic environment, measurements indicate an induced magnetic response that is best explained by a global layer of electrically conductive fluid. The most natural candidate is a salty liquid water ocean. This is important because it is not a maybe we saw something shiny kind of evidence. It's physics. Conductive fluid plus changing magnetic fields produces a measurable effect. How much water are we talking about? Models suggest Europa's ocean could be tens to over 100 kilometers deep. Depending on the exact thickness, Europa may contain more liquid water than all of Earth's oceans combined. That fact is not a promise of life, but it is a reminder that Europa is not a small puddle. If it is wet, it is profoundly wet. The big uncertainty: how thick is the ice shell? Ice thickness estimates vary widely, often quoted in the range of a few kilometers in localized thin areas up to tens of kilometers globally. Thickness matters because it controls exchange. A thinner shell makes it easier for ocean material to reach the surface and for surface oxidants to reach the ocean. A thicker shell can isolate the ocean, potentially limiting chemical energy and making sampling far harder. One of the main jobs of the next generation of missions is to constrain this thickness and identify regions where the ice may be thinnest or most geologically active. The quiet engine, tidal heating, and why Europa can stay warm. Europa is far from the sun, so sunlight alone can't keep an ocean liquid. The key heating mechanism is tidal flexing, how Jupiter keeps Europa warm without touching it. Europa's orbit is slightly eccentric, and Jupiter's gravity is immense. As Europa moves closer and farther in its orbit, tidal forces change, flexing the moon. Flexing causes internal friction, and friction produces heat. This is tidal heating. This same family of physics drives extreme volcanism on Io, another Jovian moon. Europa is less violently expressive than Io, but it may use that energy to keep an ocean liquid and to drive ice shell dynamics. Why energy matters for life. Life needs more than warmth. It needs usable energy, usually in the form of chemical disequilibrium, meaning chemical gradients that can be exploited by metabolism. On Earth, some ecosystems are powered entirely without sunlight, using chemical energy at hydrothermal vents or within rock-water interactions. Europa could, in principle, offer similar energy pathways if its ocean interacts with rock, and if oxidants or other electron acceptors can be supplied. The chemical question: does Europa have what life needs? Water is the headline, but chemistry is the quiet detail that decides everything. The essential ingredients. Life as we know it uses elements such as carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, plus trace metals. Europa obviously has hydrogen and oxygen in water. The deeper questions are: is there enough accessible carbon in useful forms? Are nutrients like phosphorus available, or are they locked away? What salts dominate the ocean, and what does that imply for pH and chemical energy? Is there sustained chemical cycling, or is the system chemically flat? Oxidants from the surface. Europa's strange advantage. Europa sits in intense radiation from Jupiter. Energetic particles strike the surface ice and can split molecules, forming oxidants such as hydrogen peroxide and potentially oxygen-bearing compounds. Radiation is harsh for exposed organics, but it may also charge the surface with chemically useful oxidants. If those oxidants can be transported down into the ocean and meet reductants produced at the seafloor, Europa could maintain strong redox gradients, one of the most life-friendly energy setups we can imagine in a dark ocean. The catch is transport. Oxidants only help life if they can reach the places where life could use them. Transport is the central unknown. A habitable Europa is not only about having ingredients, it's about mixing them. Key questions include: does the ice shell cycle material downward in a way analogous to subduction, even if it's not Earth-like plate tectonics? Do certain terrains, like chaos regions, represent sites of partial melting, upwelling, or exchange? Are there brines within the ice that can move chemicals? How often does ocean material reach near surface depths? Answering these questions is one of the main scientific motivations behind mapping Europa in detail, rather than just taking a distant photograph. Surface radiation, destructive to biology, useful to chemistry. Europa's surface is a difficult place for life as we know it. Jupiter's radiation belts bombard it with energetic particles that can damage and break apart complex organic molecules. Why surface samples can be misleading. If you scoop the topmost ice, you may mostly get radiation-processed material chemistry that has been altered, broken down, or reassembled in ways that obscure its origin. That makes direct biosignature hunting on the surface challenging unless the material is very fresh or protected. Why radiation still matters in a positive way. At the same time, radiation can produce reactive oxidants that may serve as chemical fuel if they are delivered downward. Europa's surface might be a chemical factory, while the ocean is the chemical consumer if the ice shell connects them. Plumes. Does Europa vent ocean material into space? Plumes are a major reason Europa captures public imagination, because plumes would allow sampling without drilling. The careful status of the evidence. Europa's plume evidence is intriguing, but not as settled as Enceladus, Saturn's moon, which has clearly observed persistent jets. For Europa, Hubble observations have reported signs interpreted as transient water vapor or plume-like features in some instances. Some analyses have connected potential plume activity to regions where tidal stresses would be expected to open cracks. There has also been continued debate and reanalysis, including work suggesting that certain signals might have alternative explanations, and work suggesting that older spacecraft data may be consistent with plume activity. The honest scientific view is Europa may plume, possibly intermittently, but we do not yet have the kind of repeated, unambiguous confirmation that would make plumes a guaranteed sampling strategy. Why plumes would be transformative? If plumes are real and accessible during flybys, spacecraft instruments could measure water vapor and its composition, salts and ice grains, organic molecules, isotope ratios that might hint at processes in the ocean. Even then, interpreting results would require caution because chemistry can be produced without biology. But plumes would dramatically increase the pace of learning. Recent major progress: JWST and Europa's surface chemistry. In the last few years, one of the most important new sources of Europa insight has been the James Webb Space Telescope. Carbon dioxide in geologically young regions. JWST infrared observations have supported the presence of carbon dioxide concentrated in certain regions, including areas associated with disrupted or younger terrain. The interpretation many researchers find compelling is that at least some of this CO2 may be linked to internal processes rather than being only external contamination. This does not prove life, and it does not automatically prove direct ocean exposure. But it strengthens a crucial habitability idea. Europa's surface chemistry may, in places, be connected to the subsurface environment. The larger implication: if internal exchange is real and ongoing in certain terrains, then Europa is not just an ocean sealed under a static lid. It may be a chemically communicating world, at least episodically. That improves habitability potential and helps identify where future missions should look. The probability question: is there likely to be life? A precise numerical probability is not scientifically justified because we have a sample size of 1 for life, Earth, but we can still speak clearly about what would raise or lower the odds in a rational way. Factors that raise the odds: a long-lived ocean lasting billions of years, providing time for complex chemistry and potential origins of life. Persistent energy sources such as tidal heating and water-rock interaction. Seafloor chemistry that generates reductants like hydrogen, sulfides, or iron-based energy pathways. Delivery of oxidants from the surface into the ocean, creating strong chemical gradients. Availability of key nutrients, especially carbon sources and phosphorus in accessible forms. Evidence of ongoing exchange between ocean and surface, which renews chemical opportunities. Factors that lower the odds: an ocean that is too isolated chemically, with weak gradients and limited mixing. A seafloor that is geologically inactive or chemically unproductive. Nutrient limitations severe enough to prevent the complexity life requires. The unknown difficulty of abiogenesis. Even with good conditions, life might still be rare. A grounded way to say it: Europa looks like one of the best places beyond Earth to have a habitable environment because it likely has water and energy. Whether life actually arose, there is an open question that depends on seafloor interactions, chemical cycling, and the true nature of the ice-ocean exchange. The next big step: Europa Clipper and what it will actually do. The most important near-term development for Europa science is NASA's Europa Clipper mission, launched in 2024 and traveling toward the Jupiter system for a detailed campaign of Europa flybys. What Europa Clipper is designed to answer? Europa Clipper is not a life detection mission in the narrow sense. It is a habitability and reconnaissance mission. Its goal is to map and measure the conditions that would control life's chances and to identify the most promising places for future-focused investigations. Key objectives include determining the thickness and structure of the ice shell, including potential pockets of liquid water or brines within it, characterizing the subsurface ocean, depth, salinity, and how it interacts with the ice and interior. Mapping surface composition, including salts, oxidants, and organic-related chemistry, searching for signs of current activity, plumes, thermal anomalies, active fractures. understanding Europa's geology to locate regions of recent resurfacing or exchange, measuring the radiation and particle environment that affects chemistry and surface preservation. Why this matters for life probability. If Europa Clipper finds strong evidence for thin or variable ice in certain regions, active exchange processes, chemistry consistent with an ocean in contact with rock, abundant oxidants, and plausible delivery pathways, then the argument for habitability becomes much stronger, and the case for a follow-on lander or sampling mission becomes more targeted and efficient. Europa in context, JUICE and the wider Jovian system. ESA's JUICE mission, launched in 2023, focuses primarily on Ganymede, but will also contribute to understanding the Jupiter system's oceans, magnetospheric environment, and comparative habitability. Comparative planetology matters. Learning why Europa, Ganymede, and Callisto differ helps isolate the key variables: radiation intensity, tidal heating strength, internal structure, and chemical evolution. Often, the fastest way to understand one world is to understand its siblings. If Europa has life, where would it be? If Europa's ocean hosts life, the most plausible habitats would be places with chemical gradients and material exchange. Likely hotspots, conceptually, the seafloor, especially if hydrothermal activity exists, interfaces where water reacts with rock, generating chemical energy, regions where oxidants delivered from the surface can mix with reductants, areas beneath geologically active terrain where exchange may be more frequent. Life might be widespread or extremely patchy. It might exist as thin microbial films, scattered communities, or sparse populations adapted to low energy. It might also be absent. How we would detect life? What would count as evidence? Life detection is rarely one silver bullet. It is usually a convergence of clues, stronger forms of evidence, complex organic molecules with patterns hard to explain by non-biological chemistry alone. Isotope ratios suggestive of biological processing. In context, chemical disequilibrium strongly maintained in a way consistent with metabolism. Repeated detection of the same suite of organics and chemical relationships across time and location. If sampling is possible, microscopic structures consistent with cells would be extraordinary. But this is far beyond what orbiting missions can typically do. Why caution is essential. Abiotic chemistry can produce organics. Hydrothermal systems can generate complex molecules without life. Radiation chemistry can create surprising products. A claim of life would require careful elimination of non-biological explanations. That caution is not pessimism. It's what makes a discovery durable, a quiet, honest conclusion to rest with. So, does Europa have life? We do not know, not yet. What we do know is that Europa likely has a global ocean sustained by tidal energy beneath an active and fractured ice shell. We have growing evidence that the surface chemistry is interesting in ways that may connect to the interior. We have plausible pathways for chemical energy, and we have a clear plan through missions like Europa Clipper to measure the key unknowns that control habitability. If Europa is inhabited, It would be one of the most profound discoveries in the history of science. A second example of life, arising beyond Earth. If Europa is uninhabited, the lesson would still be immense, because it would tell us that water and energy are not always enough, and it would sharpen our understanding of what life truly requires. Europa continues to orbit Jupiter in the dark, patient and unchanged by our curiosity, and that patience can be calming. The universe does not rush answers. It reveals them slowly through physics, observation, and time. As you listen and your breathing settles, it can be enough to hold a simple thought. Somewhere under Europa's ice, an ocean may be moving in complete darkness, warmed by gravity, shaped by chemistry, and waiting for us to learn how to ask the right questions in the right way. Sweet dreams.